Hello grade 10s and welcome to the lesson. Today we are going to be looking at the cast diagram and working on the Cartesian plane. We're going to be looking at angles on the Cartesian plane. And as I've noted here at the bottom of our screen, please have activity 5 printed or a digital copy to work on for today's lesson, because we are going to be filling in things together as I work through the video. So please have that available so that you can work on your own copy. Whether it's a hard copy, printed, or a digital version, both will be fine. So in this section, we are going to extend the trigonomic definitions to include angles between 0 and 360. All right, so what you'll see here is I've started already labeling quadrants, popping in things like theta, 180 minus, 180 plus, these big letters. By the end of the section, this will make complete sense, and we will come back to this slide at the end of the video. But let's talk about a few important concepts first. So our Cartesian plane starts with 0 degrees here on the positive x-axis, all right? We know that this is our x-axis and this is our y-axis. So we start with 0 on the positive x-axis and we move anti-clockwise to 90 degrees. This area here is called Quadrant 1. From 90 degrees to 180 degrees, this is called Quadrant 2. From 180 to 270 degrees, this is Quadrant 3, and angles from 270 to 360 degrees, this would be called Quadrant 4. So you notice how we move in an anti-clockwise position for positive angles on the Cartesian plane. So here I've labeled the origin O, and I've drawn this terminal arm, right? That's the name we give it. So a terminal arm is just linking the origin with a point P on the Cartesian plane. Remember that a coordinate is made up of an x value and a y value. And what we're going to do is we are going to create right-angled triangles by dropping a perpendicular from that point to the x-axis. Why would I want to have a right-angled triangle in trigonometry? Well, don't we need the right angle to be able to label the hypotenuse? And then from our reference angle, find the adjacent and opposite sides. Yes, exactly. We want to be working with a right-angled triangle. But we are now not going to be always using the words adjacent, opposite, hypotenuse. We are now also going to be starting to talk about sides in terms of x, y, and the letter R. All right, but let's jump into the first page of our activity so that we can really explore this in depth. All right, so let's have a look. Remember that this is an investigation. So at first, maybe it's a bit like, I'm not too sure what's happening. But as we keep moving through the activity, hopefully all of it will start to make lots of sense. Okay, so we're going to start off by working in Quadrant 1. All right, so remember I said Quadrant 1 is between 0 and 90 degrees on the Cartesian plane. We'll notice here, so they've labeled the terminal arm with A being the origin, right, and C being a point on the Cartesian plane. So let's read what this point is. So here I can see that x is 3 and y is 4. Okay, so the coordinate of C is 3, 4. All right. So here I have a right-angled triangle, A, B, C. So perhaps let's just fill in the lengths. So the length AB would be 3 units. The length BC would be 4 units. Now, I need to figure out the length of AC, right? I need to figure out the length of the hypotenuse so that I've got all 3 sides. And how can I find the hypotenuse? Well, we're going to use good old Pythagoras, hey? So the hypotenuse squared is equal to side squared plus your second side squared. So the hypotenuse squared will be 3 squared plus 4 squared. All right, that's going to equal 25. So the hypotenuse will be 5. All right, so now I know some of you were saying, Claire, when I square root, shouldn't I get plus or minus as a solution? Shouldn't the answer for square root 25 be plus or minus 5? And I would say you are 100% correct. But this is a length, right? And if you're dealing with length, if you're dealing with the measurement of a length, this must always be positive, all right? So the hypotenuse is always positive, this terminal arm here. X and Y, however, depending on where I move onto the Cartesian plane, your X and Y values can be negative, but because they are a length, right? Like 3 is a length, but it's also discussing its position on the Cartesian plane, right? Whereas this is the hypotenuse, this length will always be positive. Okay, so that's very important to remember. Okay, so let's get to labeling our sides. From the reference angle, right, the length 4 would be your opposite length, 3 would be adjacent, and that 5 on the terminal arm, well, that's the hypotenuse. But now, since I'm working on the Cartesian plane, since I'm working on an x-axis and a y-axis, I kind of want to change the way I'm naming the sides. So when you're just working in any old right angle triangle, right, that's not on the Cartesian plane, you've just drawn it yourself, or you're solving a right angle triangle, using adjacent opposite hypotenuse is perfect. But remember that we are working on the Cartesian plane, right? We're working on an x and a y axis. We are imagining a circle being drawn around here, right? Where we connect the origin to that point on the circumference, which we call the terminal arm. So talking about adjacent opposite hypotenuse is fine, but when I'm working on the Cartesian plane, I want to rename my lengths. So this length along the x-axis, well, obviously, we're going to call that length x. This length running parallel to the y-axis, right, which we have as opposite at the moment, we're going to call that length y. And the hypotenuse, we are going to label that length as the... So we can't say hypotenuse anymore. We're instead going to use the letter R, right? R for radius. So don't think now, why are you confusing me like this? You're throwing all these extra things. I just got used to opposite, adjacent, hypotenuse. It's exactly the same, great sense. And it's easy to remember. The length along the x-axis will be labeled as x. The length parallel to the y-axis will be labeled as y. And your third side, the hypotenuse, you're just going to label with the letter R. Okay, so don't let it trip you up. It's still nice and easy. So let's actually answer, we'll fill in what they want us to fill in. The ratios of the following trigonometric functions in the first quadrant are. Okay, so from the reference angle, right, sine, normally we would say opposite over hypotenuse. Using these new letters, sine is y over r. All right, so sine of theta is y over r. And I think there's not really enough space there, but let's write down what this ratio actually is using the numerical values. So 4 over 5. So in this diagram, sine of theta, y over r is equal to 4 over 5. And tell me, is this ratio, is this fraction, is that positive or negative? Well, clearly we can see that that is positive. So your function, your trigonometric function for sine is positive in quadrant 1, which makes sense because even if you looking at y over r, right, your y value will always be positive in quadrant 1 because you're on the positive y-axis, and we know that the hypotenuse, your terminal arm r, that is always positive because it's a length. So a positive over a positive, well, that makes a positive. if we deal with cosine, with cos. So cos is usually adjacent over hypotenuse, but using our letters, x over r. So cos of theta is equal to x over r. And if we write down the numerical value of that, right, a x3 over h r, or 5. So your ratio that you form here is 3 over 5. And tell me, is 3 over 5 positive or negative ratio? That is also positive. And again, it makes sense. This is on the positive x-axis, so of course this value will be positive, and the hypotenuse or terminal arm is always positive. And a positive over a positive, well, we know that that's just a positive. If we look at our third trig function, tan. So tan is usually opposite, or is opposite over adjacent, but let's use our letters. So tan will be y over x. So tan theta is y over x. And using the given values in our sketch, that would be 4 over 3. And tell me, is 4 over 3 a positive or negative ratio? You got it, it's positive. So what have we noticed now about quadrant 1? All 3 of my functions are positive. Isn't that nifty? Let's investigate what's happening in quadrant 2. So they gave us that same triangle. It's just been reflected over the y-axis. So I now have the coordinates -3, 4, right? I can see I'm at -3 on the x-axis, and 4 is my corresponding y value. So that C point is -3, 4. Let's label our triangle the same way as we did previously. So this length AB, right? So that is the length which we can label x. But you see that in this quadrant, I am on the negative x-axis. So that length we're going to label as -x, and that is -3. The length BC, right? The vertical length parallel to the y-axis. Well, since I'm parallel to the positive y-axis, I'm going to leave that length as positive y, and that is going to be positive 4 units. The length AC, so your terminal arm, we label that now with the letter R, the hypotenuse, and we are going to determine that that length is 5, just as in my previous triangle. If I verify that with you, we know that the hypotenuse squared is the side squared plus the second side squared. So you square that -3. So it becomes +9, all right? So you don't say 16 minus 9, it's 16 plus 9. And our hypotenuse, as I said before, is always positive. All right, so we have been talking about opposite adjacent hypotenuse up until now, but really in this investigation, we really want to use these letters x, y, and r. Remember that x and y will either be positive or negative depending on which quadrant I'm in. So in quadrant 1, where the x-axis was positive, right, we're on the positive x-axis, the positive y-axis, your x and y value will be obviously positive. However, I'm now on the negative x-axis and the positive y-axis. So now my x values are negative, whilst the corresponding y values will be positive. Remember, hypotenuse, terminal arm, always positive. Right, so let's start figuring out. In quadrant 2, how would I write sine of theta? So sine would usually be opposites over hypotenuse, but since we're working on the Cartesian plane, we're going to say that that is y over r. If I had to write down the actual lengths, that would be 4 over 5. So is the ratio 4 over 5? Is the fraction 4/5 positive or negative? Well, clearly that would be positive. Let's move on to cos or cosine. So cos is adjacent over hypotenuse, but since I'm on the Cartesian plane, I'm going to say negative x over r. So negative x over r. If I write down the value of that using the given lengths that we've determined, that's negative 3 over 5. So we've come and found the first ratio to be negative in this investigation so far. So in quadrant 2, your ratio of cos is negative. Let's see what's going to happen with tan. If I look at tan, well, we know that tan is opposite over adjacent, but since I'm on the Cartesian plane, y over negative x. Y over negative x. And if I write down those lengths, it's 4 over negative 3. So clearly, again, we can see that this ratio is negative. So something very interesting has happened in quadrant 2. In quadrant 2, your only function that was positive was sine. Your other two functions, cos and tan, were negative. Compare this to quadrant 1, where all three of the functions were positive. But this makes sense, right? If you look at how we express the ratio, negative x over r, you are dividing a negative by a positive. So obviously the result is that your entire ratio would be negative. And the same is happening for tan. All right, so we've come with some very important deductions. In quadrant 2, sine is positive, whilst cos and tan are negative. Something to mention before we move on, because a few of you might have been thinking about it already. A few of you might be thinking about, Claire, didn't you tell me in quadrant 2 that the angles formed are between 90 and 180 degrees? If you look at your reference angle grade 10, there's a reference angle. Does that look like an angle between 90 and 180 degrees? There's no ways that that angle is between 90 and 180, right? Remember that this is a right-angled triangle, so the two remaining angles themselves must add up to 90. You can't have one angle which is bigger than 90. That doesn't make sense. So what is going on here then? The angle which is actually formed starts from the positive x-axis and moves anti-clockwise until it touches the terminal arm. So this is actually the size of the angle which is formed. And that, I'm sure you can agree with me, that it has gone past 90 degrees, past the right angle. So this is an angle between 90 and 180 degrees. And what we're going to do is later on, we are going to learn how do I reduce this angle to make it acute so that it will fit inside a right-angled triangle. All right, because remember, we want to be working in right-angled triangles so that I can use the ideas of opposite, adjacent, hypotenuse, also that I can draw this triangle in the Cartesian plane and have negative x, y, and r. All right, so this is actually the size of the angle which is formed, and later on I'm going to show you, well, how do I get this big old angle and just manage to squish it into the right angled triangle. Okay, let's move on to quadrant 3. All right, so here's our quadrant 3. Let's just fill in. There would be our right angle. There's theta over there, the reference angle. And if I now talk to the stuff that I was just mentioning, right? The size of the angle actually formed, because now you can see that your angles are going to be between 180 and 270 degrees. The size of theta is actually from the positive x-axis. We go anti-clockwise till we touch that terminal arm. That's the size of theta. So you'll agree with me. This has gone past 180 degrees, right? Past your straight line. And now I'm between 180 and 270. So that's the full size of your angle. But what we do is, and I'm going to teach you later on how we do this. We make that big angle, we reduce it down to an acute sized angle, which then fits in this right angled triangle. Okay, but we're going to learn about that later on. let's start a labeling. Well, what's this coordinate? Here x is -3 and y is -4. And let's then label our x value. So we figured out that the x value is negative, so that's going to be negative x. We're on the negative y-axis, so that length BC will be negative y. And remember that the hypotenuse, your radius, the length r, is always positive, so that we write as positive r. Let's fill in those values. So this is going to be -3, this is going to be -4, and guess what? Using Pythagoras, that is going to be 5. All right, if I verify quickly, the hypotenuse squared is side squared plus side squared. So we've seen this now, third time around, hey? Your hypotenuse is equal to 5. Okay, so the lengths we're dealing with here in this quadrant, -3, -4, and 5. All right, so let's fill in then sine of theta. So sine is opposite over hypotenuse, or on the Cartesian plane, in this case, negative y over r. So negative y over r, that is -4 over 5. Right, so that ratio, that fraction is negative. So it's the first time I've noticed that my trigonomic function sine is negative. When I was in quadrant 1 and 2, sine was positive. It's the first time now in quadrant 3 that I see that it's negative. Right, what about cosine? What about cos? So cos is adjacent over hypotenuse, or if we work on the Cartesian plane, negative x over r. All right, so in quadrant 3, cos is negative x over r, -3 over 5. Well, that ratio, that fraction is also negative. So far, cos has been positive in quadrant 1, negative in quadrant 2, negative in quadrant 3. I wonder what's going to happen in quadrant 4. But let's focus here. What about tan? So tan would be opposite over adjacent, negative y over negative x. So negative y over negative x. Well, two negatives, if we're dividing, that just becomes positive, right? That would just be y over x. So that fraction would be -4 over -3, which becomes 4 over 3. So we can see that in quadrant 3, tan is positive. So tan is positive whilst cos and sine are negative. So this is really interesting. In quadrant 2, I had one function positive, two functions negative. In quadrant 3, the same thing has happened. I've had one function, tan, positive, whilst the other two were negative. Okay, so let's think now. What do I think will happen in quadrant 4? Cool, so we're really in the swing of things now. Let's label our point. Now x is positive. Your y value is negative. So that's going to be +3, -4. Our x value, right, the length we'll label as positive x in this case because we're on the positive x-axis, and that length is 3. This length will be -4, right, parallel to the negative y-axis, and our hypotenuse, the radius, right, is going to be 5 using Pythagoras again, which I won't show you because we've done it 3 times, and yes, I'm sure you believe me by now. All right, this is where our 90 would be. There's our reference angle, and just out of interest sake then, the angle formed started from the positive x-axis, it moves anti-clockwise, so this is actually the size of theta. And what we do is we take this big angle right now between 270 and 360 degrees, and we reduce it down to this acute angle inside the right angle triangle, which I'm going to show you later on how do I do that. Okay, but for this exercise, remember what we're doing is we're just labeling our sides and writing down the ratios for each of our functions. Okay, so for sine, right, so from the reference angle, sine is opposite over hypotenuse, and since I'm on the Cartesian plane, I'm going to say negative y over r. So sine is negative y over r. So negative 4 over 5. So that ratio, that fraction is negative. What happens with cos? So cos is adjacent over hypotenuse, but since I'm on the Cartesian plane, x over r. Oh, this is interesting. Cos is positive in quadrant 4. So that ratio would be 3/5, which is... Let's see what's happening with tan. So tan, right, from the reference angle, tan is opposite over adjacent, negative y over x. So negative y over x, so that's going to be negative 4 over 3. So that ratio, that fraction is negative. All right, so again, I've noticed that in this quadrant, there are two functions which are negative, whilst the one function is positive, right? And that has happened throughout your Cartesian plane, except for quadrant 1. In quadrant 1, all your functions are positive. And then as you move into the different quadrants, two of the functions will be negative, whilst the other function is positive. But overall, each function will be positive in 2 quadrants and negative in 2 quadrants. So that we can summarize nicely over here. If we look at quadrant 1, right? Remember that in quadrant 1, you had a positive x and y value, and we know that the hypotenuse, the radius, was always positive. So in quadrant 1, the ratios which were positive were all 3 of them, right? Sine, cos, and tan were all positive in quadrant 1. In quadrant 2, right, so that's the angle which is formed. Remember, we reduce it down to this little acute angle there, and we'll explore that reduction later. But in quadrant 2, so the coordinate here would be x is negative, y is positive, the hypotenuse, your length r, is always positive. So in quadrant 2, we found that it was only sine which was positive, right? Because our ratio for sine is y over r. So for cos and tan, since they use that negative x in their ratio, in their fraction, those ratios always came out as a negative. So only sine is positive in quadrant 2. All right, what about in quadrant 3? So in quadrant 3, your x and y coordinate were both negative. Your hypotenuse, your length r, is always positive. And we found in quadrant 3, it was only the function for tan that came out as a positive, because we divided the two negatives over each other, which made the ratio positive. So in quadrant 3, tan is my positive ratio. In quadrant 4, your x value is positive, but your y value is negative, right? Because of our position on the Cartesian plane. And we know that our hypotenuse, the radius, is always positive. And in quadrant 4, the ratio which was positive was cos or cosine. Right, that was the one which came out as a positive. So as I mentioned previously, you can now quite easily see, so beautifully illustrated here, how the functions are positive in 2 quadrants. So sine is positive in quadrant 1 and 2. Cosine is positive in quadrant 1 and 4, and tan is positive in quadrant 1 and 3. So your functions are positive in 2 quadrants and negative in 2 quadrants. All right, grade 10. So now we're really going to get stuck in, and we're going to look now at reduction formulae, and I'm going to explain how did I take those angles which were bigger than 90, bigger than 180, bigger than 270. How did I take those angles and make it that they were small enough to fit into a right-angled triangle? And we are going to be focusing in this first page here. We are just going to be working in quadrant 2, right? And here it says in quadrant 2, we use 180 minus theta. Now, I'm going to bring up that slide from the start of the video so we can see and explore this idea a little bit more. So here's my cast diagram from the start of the video, and hopefully now looking at this, a lot more stuff is making sense, right? First of all, my different quadrants, my terminal arm, plotting a coordinate, and creating a right angle triangle. We are working in quadrant 2. You'll notice here I have this big letter S, and I've also written 180 minus theta. All right, so 180 minus theta. And some of you might be going, okay, what's this about? Let's look at the angle that they gave us to start with. They gave us 120 degrees. Do you agree with me that 120 degrees is definitely in quadrant 2, right? Quadrant 2 is angles between 90 and 180. So 120 degrees definitely falls into quadrant 2. Your job is, how can I rewrite 120 as 180 minus something, right? And this something being an acute angle. So how can you rewrite 120 degrees using 180 minus? Right? If I say 180 minus, well, obviously 60 degrees, those are equivalent. They both say 120. They both read 120. But now what happens is you reduce down to that acute angle that we figured out. So sine of 120 is the same as sine of 60. This is its reduced version, right? Where the angle that we create is acute in size. Why do I want it to be acute? So that I can work in my right angled triangle, so that I can figure out my ratios. So it's very important that we take this bigger angle and reduce it down to an acute sized angle. So sine of 120 in quadrant 2 is equivalent to sine of 60, which is root 3 over 2. Right? That's I read up from over there. Or if you just punch this into your calculator, or using our special triangles, we get that sine of 60 is root 3 over 2. Now I have cosine 120, or cos of 120 degrees. So still, it's 180 minus 60, right? That's my equivalent angle. This still reads 120 degrees. When I simplify, though, this now says negative cos 60. But why is it negative? And the same for, why is tan negative, cos negative, but sine is positive? Well, remember, in quadrant 2, that's the quadrant where sine is positive. So that's what the S is standing for, sine. In quadrant 2, sine is positive. That's why there's an A in quadrant 1, because in quadrant 1, all the trigonomic ratios are positive. So in quadrant 2, the trigonomic ratio of sine is positive. All right, so cosine and tan in quadrant 2, they are negative. We've proven that already in the investigation. Then if I type cos of 60 on my calculator, it's a half, but it's negative cos 60, so it's a negative half. Negative tan 60 is negative root 3. All right, so this is the skill that we use in our grade 10s. We're going to take our angle, because we're working in quadrant 2, the 180 minus theta quadrant, we're going to rewrite our angle as 180 minus an acute sized angle, and that is what we're going to reduce down to. All right, let's check with 135 degrees. Okay, so now we're dealing with this angle over there, 135 degrees, and we just need to fill some more information in on this sketch of ours, right? So let's put in the size of the angle formed. So from the positive x-axis to that terminal arms, we form an angle of 135 degrees. Now we need to figure out what will that acute angle be inside my right angle triangle. And I know some of you are very bright. You already know what the answer is going to be. But let's work together. So we're in quadrant 2, the 180 minus theta quadrant. I know that I'm in quadrant 2 because 135 degrees Do you agree with me that 135 degrees definitely lies in this area, right? It lies between 90 and 180 degrees. If I take 135, how can I rewrite 105 as 180 minus something? 180 minus an acute-sized angle must be equivalent to 135, and obviously that then must be 45 degrees, right? 180 minus 45, well, that is 135 degrees. So the acute angle, which you now form in your triangle, will be 45 degrees. Isn't that nifty? So you've reduced that angle, which was too big. You've reduced it down using that concept of 180 minus theta. You've reduced it down to the acute angle of 45 degrees. So now we get to this bit over here, where we're going to rewrite sine 135 in terms of 45. We need to identify first, is the function positive or negative? We're in quadrant 2. That is sine's positive. So in quadrant 2, sine is positive, but cosine, cos, and tan are negative. So this is going to come out as a positive, this will be negative, this will be negative. All right, we've already established that sine 135 we can reduce down to sine of 45. Cos 135 will be negative cos 45. Remember, it's negative because we're in sine's quadrant. Quadrant 2 is where sine is positive, but cos and tan are negative. So tan 135 will be negative tan 45. All right, and then we just have to write down, so what is the value of that? What is sine 45? So sine 45 is root 2 over 2. Right, you can verify that on your calculator, or we draw our special triangles and we can figure that out. Cos 45 is equivalent, but remember that it's negative in quadrant 2. So it's negative root 2 over 2. And tan of 45, that one's easy. Tan of 45 is just negative 1. All right, so we've taken the angle, which is too big for my right angle triangle. We've reduced it down. So what was the steps? You have to identify the quadrant you're in. Is the function positive or negative in that quadrant? And then we reduce it down to its acute angle. All right, and then once we've got that acute angle, we can relate that to our special triangles or these special angles, which 45 degrees, 30, and 60 degrees form. Okay, let's go on to the 150 degree one. All right, so let's look at our last one, 150 degrees. So I'm just keeping the cast diagram here. I love referring to this all the time in trig. This is going to become super useful, handy, and you're going to use it a lot more moving forward in your trig. So I'm going to keep it here while we keep discussing. So the next thing we need to do is 150 degrees. Okay, so 150 degrees. You'll agree with me that 150 degrees falls between 90 and 180, right? It falls into that area. That's in quadrant 2. Quadrant 2 is 180 minus theta quadrant. So how can you rewrite 150 as 180 minus something? Well, you should be saying it's 180 minus 30, right? That is equivalent to 150 degrees. So now we can fill in our sketch at the bottom here. So our angle is 150 degrees, and the equivalent angle that we get in our right angle triangle once we apply our reduction formula is 30 degrees. So now sine of 150 we could rewrite as positive sine of 30. Remember, it's positive because we're in quadrant 2. So cos 150 will be negative cos 30, and tan 150 will be negative tan 30. All right, and now all we need to do is write down what those ratios are. So sine of 30, well, that's a half. All right, so sine of 30 becomes a half. Negative cos 30, that'll be negative root 3 over 2. And tan of 30, That's going to be negative root 3 over 3. That you can verify and check on your calculator. But yes, so those would be the numerical values for those three trigonometric functions. Isn't it super interesting? All right, so we've done some beautiful reduction formula here. We've just been focusing on working in quadrant 2. So let's summarize then what we have learned. That in quadrant 2, if it's sine 180 minus theta, it comes out as positive sine theta. Right? Remember that theta is that acute sized angle we've reduced down to. For cos and tan, however, since we are working in quadrant 2, the functions are negative in those quadrants, well, is negative in quadrant 2. So cos 180 minus theta will be negative cos theta, and tan 180 minus theta will be negative tan theta. Awesome. So we are just going to explore now what's going to happen in quadrant 3 and 4. Okay, awesome. So I'm going to move a bit quicker now through our next page, working on quadrant 3. Let's just fill in. So we know now that this S stands for sine, this A stands for all. What do you think T is going to stand for, grade 10s? It's going to stand for tan. And guess what? C, it's not for Claire. C is for cos. So now you're getting a feel for what is the CAST about. And also this is why we call it the cast diagram, CAST. All right. So in quadrant 3, where we're working now, tan is going to be positive, but sine and cos, we should see, will come out as negative. This is also the 180 plus theta quadrant. And now our angles lie between 180 and 270 degrees. As we see with our first example, 240. So let's have a look. There's the size of the angle, 240. They've reduced it down to 60. How did they land up at 60? This is 180 plus some angle. So we are dealing with 240 degrees, right? Which definitely lies in this region. So 180 plus what is 240 degrees, right? And you should all obviously be going, well, I know that 180 plus 60 is the same as 240 degrees. So that's then how they reduce down to the acute angle 60. So if we look at sine of 240, so that's the same as 180 plus 60. So we reduce down to sine of 60, but because we're in quadrant 3, which is tan's quadrant, sine is negative. Cos 240 is the same as cos 180 plus 60, which reduces to cos 60, but remember, because I'm in quadrant 3, it becomes negative cos 60. Then for tan, because I'm in quadrant 3, 180 plus 60 reduces down to tan of 60, and it is positive since I'm in tan's quadrant. All right, and then we know what these values are from the previous quadrant that we were working in, right? Sine of 60 is root 3 over 2. Because we're in quadrant 3, negative root 3 over 2. Cos of 60 is a half, but we're in quadrant 3, so negative a half. And tan of 60 is now positive, so positive root 3. So now as we move on to our next two angles, 210 and 225, you should be finding this a lot simpler. Right, so now we're looking at 210 degrees. How can I rewrite 210? 180 plus what is the same as 210? Remember, I'm going 180 plus because I'm in quadrant 3, the 180 plus theta quadrant, and I know that I'm working in quadrant 3 because 210 lies between 180 and 270. So 180 plus 30 is equivalent to 210. So sine of 210, well, let's go through the steps. I'm in quadrant 3, so sine is negative. That's the 180 plus theta quadrant, so 180 plus 30. So when I reduce it down, it becomes negative sine of 30, which is a negative half. All right, that's really it. Grade 10s, you're on it now. So cos 210, right, in quadrant 3, cos is negative, it reduces down to cos of 30, which is negative root 3 over 2. Tan of 210, well, tan is positive in quadrant 3, so that reduces down to tan of 30, and tan of 30 is equal to root 3 over 3. All right, so let's just fill in the rest of our sketch, though. Got a bit ahead of ourselves. I was so excited. So this is now 210 degrees, and the acute angle formed where that little green dot is 30 degrees, right? That's the angle over there. All right, let's look at 225. Well done, guys. So we're cruising now. 225. So 225, we need to rewrite as 180 plus something is equivalent to 225 degrees. So I know that if I add 45 degrees, so the angle here in our sketch, this will be 225, and the little acute angle that we form, that's going to be 45 degrees. All right, so that's kind of the hard bit, because now it's actually really easy, because I go, all right, sine 225, 225 degrees, quadrant 3. In quadrant 3, my function is negative, so negative sine. What was the acute angle which we reduced down to? Well, we figured out it was 45 degrees. And then that just simplifies to negative root 2 over 2. Cos 225. Well, cos is negative in quadrant 3. The acute angle it reduces down to is 45. Hey presto, that is also negative root 2 over 2. And tan 225, well, tan is positive in quadrant 3. We don't have to write the positive. And we know that it reduced down to 45. And tan of 45 is just 1 over 1, or just equal to 1. Okay, so in summary, sine 180 plus theta is negative sine theta. Cos 180 plus theta is negative cos theta, whilst tan is positive. All right, so all of this, the 180 plus theta, right, all of this is actually saying we're in quadrant 3. So which function is positive in quadrant 3? Which functions are negative in quadrant 3? All right, that's it. Last one, let's go. Amazing. Well done, superstars. We're on the last part of this investigation. Well done. You've done so wonderfully so far. Let's just wrap this all up. We're moving into quadrant 4, right? We're moving into angles that are between 270 and 360 degrees, as our examples illustrate, 300, 330, 315. This quadrant isn't a 180 plus or 180 minus, but rather a 360 minus theta. So we go 360 degrees and we subtract that acute angle to work in our right angle triangle. Okay, so we're going to be working here in quadrant 4, and we've now determined how this is cos's quadrant, meaning cos is positive in this quadrant, while sine and tan are negative. So they started with 300. Sine of 300, they rewrote as negative sine 60. So negative because we are negative as a function in quadrant 4, if you are sine. 60, so remember quadrant 4 is now 360 minus. So it's saying rewrite 300 as 360 minus something. So if you rewrite 300 as 360 minus, well, obviously 60, that would be equivalent. So that's how we got to negative sine 60. So cos of 300, cos of 60, tan of 300, negative tan 60. So tan and sine are negative in quadrant 4 because that belongs to cos. It's cos's quadrant. It's where it's positive. And then just the ratio for 60, negative root 3 over 2. For cos of 60, a half. And for negative tan 60, negative root 3. So let's then look at 330 degrees. So 330 degrees, let's fill in our sketch. So that's the size of the angle from the positive x-axis anti-clockwise. What is that small angle going to be in there? So ask yourself, I need to write 330 as 360 minus something. right? Remember, we're in quadrant 4. So if I say 360 minus 30, that is the same as 330, right? 360 minus 30 is the same as 330. So that little angle in there is going to be 30 degrees. So sine of 330, quadrant 4, so it's negative, and it reduces down to 30 degrees. Cos of 330, cos is positive in quadrant 4, and it reduces down to cos 30 degrees. Tan of 330, well, tan is negative in quadrant 4, and we, using our reduction formula, we reduce down to negative tan 30. All right, and now we just simply fill in the value of that. So negative sine 30 is a negative half. Cos of 30 is positive root 3 over 2. And negative tan 30 is negative root 3 over 3. Hey, this is not so bad. This is pretty easy, actually. Hey, okay, let's just look at that last one, 315. So let's just fill in the last diagram. Okay, so now we're working with 315 degrees. We know we are in quadrant 4 because 315 degrees lies between 270 and 360. This is the 360 minus theta quadrant. So 315 can be written as 360 minus what? So you should be saying, well, 360 minus 45 is equivalent to 315. So let's fill that in our sketch. So this is now 315, and the little equivalent angle we found inside the right angle triangle is 45. So tan of 315, oh sorry, let's start off with sine. Sine of 315. So sine is negative in quadrant 4, and it reduces down to 45 degrees. Cos is positive in quadrant 4, reduces down to 45, and tan is negative. If I now write down the value of that ratio, so this is going to be negative root 2 over 2, this will be positive root 2 over 2, and tan 45 will simply be minus 1. All right, so grade 10s, let's just summarize then what happens in quadrant 4. When it's sine 360 minus theta, it becomes negative sine theta. Cos is the one function which is positive in quadrant 4, whereas tan 360 minus becomes negative tan theta. All right, so well done, grade 10s. We've now explored our Cartesian plane in quite amazing and beautiful detail. We've focused on the 4 different quadrants, right? Quadrant 1, 2, 3, and 4. We've now determined that it's called the cast diagram, C-A-S-T, moving anti-clockwise. C for cos, where cos is positive in quadrant 4. A for all positive in quadrant 1. Sine is positive in quadrant 2, and tan is positive in quadrant 3.